Senthil. Hello, everyone. So as Senthil said, I'm Florian. I'm a PhD candidate in Luxembourg here, under the supervision of Christophe. And today I'm going to present the framework of statistically enhanced learning, which is a work that I'm conducting with Christophe and Andreas Grohl from the University of Dortmund. And it's about how to use statistical quantities and statistical variables to improve learning in a general sense. I'm just going to go through the definition of what I mean by learning here. Just going through a quick introduction of what, in the context of what learning means, and then going through the literature, see how already exists, and then see the formalization, because our work is a formalization of all of the different techniques that already exist. And then we also try to derive some properties based on information theory to prove the benefit of those techniques. And I will conclude with an application to handball games predictions. So in the context, what we mean by learning here is that I think you all know the term of artificial intelligence, which can be a very large term to include everything which is rule-based and any kind of computer-based calculations. And what we mean by learning is whenever you have data coming in the picture, when you start having models. So it includes traditional statistical and linear models that we all know that have already been mentioned earlier today or even yesterday. But it also includes more recent fields of machine learning or deep learning. All of these are included in the sphere of learning, and that's what we are considering as a global context here. So feature engineering for any kind of model we use, is either statistical models, deep learning, or machine learning, is a very important step, because whatever you do with your model, if you don't have good quality data and well-prepared data, the result of your model and the performance of your model will just be bad because of the quality of the data. And unfortunately, it's a field which is not super well explored yet, because most of the focus is put on the actual modeling, which is potentially more interesting for most of the scientists. Just as an illustration, if you go on the well-known Stack Overflow platform and you search for the top 15 questions when you search for data preparation, or if you search for machine learning, the number of views is completely different. You have something like 43 times more views for machine learning compared to data preparation, which just shows the focus that is put on the actual machine learning. And just for the anecdote, I've tried data preparation, which is the most, which is the keyword that gave me the most views, because if I look for feature engineering or specific keywords in feature engineering, the number of views goes drastically down. So this is more to illustrate on how people actually and practitioners are looking into modeling and data preparation, but it also translates in the literature. Most of the focus is put on the modeling. Also, the term feature extraction is also used in literature, where it consists of a way to include more variables and more information in the model. In particular, if you think of unobservable variables or variables that you cannot measure, this is where you may use some kind of feature extraction techniques. So in particular, for example, if you think of sports, one important variable that we need to consider when we do a model, we need to consider, for example, stress of a player or the fatigue of a player, which is a very important aspect of the game, but it's something you cannot measure. So you may go through other techniques to approximate and take a proxy for these kind of techniques, these kind of variables, and include those into your model later on. It also applies the same for economics, where you have very known issues with, for example, the willingness to pay or the income that are not necessarily available to anyone, and you need to find another way to include those information into your model. So the idea here is whenever you include those quantities in your model is to still improve your model by capturing some information and being able to make your predictions later much better than what you would do without those quantities. So for example, for non-observed and unobservable variables, you have some techniques that are instrument variables or proxy variables that are commonly used. But you can also think of making transformation of existing data that you have, that you observe, and transforming them to extract the actual information you want to have, and then later include that into the model. And that's what we call the framework of statistically enhanced learning, because all of the quantities that we're extracting can be considered as statistical quantities, and we use them to enhance and improve the actual learning, so the model that we want to build. And that's what we're trying to formulate here. So if you think of the existing literature, our contribution was to define a taxonomy of what already exists. So if you think of this tree, for example, the idea was to take all of the different techniques that are spread across the literature without specific connections and just show that they are actually connected. And we just clustered them by type of data. You have images, for example, you have text or tabular data, and all of those fields, in a way, use different techniques to enhance their learning with different ways. If you look a bit carefully, for example, you may realize that you have some techniques like just taking moments. So you have a variable in your data set on which you compute the mean, for example, and the variance, and then these means and variances, you put them into your model. So that's possible in image data for computer vision. I'm just going to illustrate that with an example in the next slide. But you also can get something similar, for example, with sequential data on tabular data, where you can also compute means and variances and include that into your model. So now I'm just going to go through 3 examples of literature that are quite different in the actual field for computer vision, natural language processing for text, and tabular data. For computer vision, we may have a first example where authors are actually interested in making predictions of spam emails. So you have a spam and you have an email where it contains images and you want to know whether it's a spam or not a spam. So the literature usually use some standard techniques for deep learning with convolutional neural network, where you just analyze the picture and try to identify specific patterns. But here the authors also used another approach, which is feature extraction. So if you take a picture, for example, here, this dog here, you can just represent this picture as a 3-dimensional matrix, for example, where you have the 3 different colors, green, red, green, and blue. And the values that you have in your matrices are just the intensity of each of the colors. So what the authors are doing here is that all of the matrices that you have for the specific picture, you can just divide them in sub-matrices and getting blocks. So for example, here, what they do is that they have some blocks, so the left side and the right side, and even in the center, where they take those parts of the pictures and compute means and actually moments, the first 2 moments, so the mean and standard deviation. And those values are used to somehow try to detect the intensity of the colors of a picture, because they start from the postulate that spam images may have less intense colors because they may be false images, so they may have a different range in colors. And they take those means and variances from the pictures and put that as additional variables in their model, and they were able to exceed the actual performance they were getting before. In another use case, if I go for natural language processing, so for text, if you want to classify a text, like any text or a tweet, for example, which was for this specific example, and to define the sentiment of a text, whether it's positive, negative, or neutral, you may use different techniques. So there are some techniques that exist that are called, for example, the TF-IDF, which is term frequency inverse document frequency, where the idea here is within a text, within a sentence, for example, you have lots of words that you take as a token, and you try to measure the frequency of appearance of each of the words and also their relative importance for the document, how much importance and information it carries through the document. You also have word-to-vec, which is a technique which are based on neural networks, where you want to represent each of the words within a text still as a vector of similar words. So you can still have a meaning and a representation of the word. And so the authors here, to make prediction of the sentiment for a text, what they do is that they combine both techniques of TF-IDF and word-to-vec and extract some quantities that are vectors actually for each of the words, and include that into a machine learning model, which is here the support vector machine, just to make the prediction. And still here, as you can guess, it improved the performance of the model. They were able to get much more interesting performance based on this technique. And finally, to a more tabular setting that we may all know, I'm taking the example here of one work that were conducted a few years back by Christophe and Andreas Grohl, where they were trying to predict football game scores, so how many goals would be scored within a game by different teams for the World Cup. And so what they did is they first tried to extract information that they wanted to measure, which would be considered as important, namely the strength of a team, which we can all agree that it's an important factor for a game to know how balanced a game will be. And to estimate that, because it's not measurable, what they do is that they get a bivariate distribution, a bivariate Poisson distribution with two parameters, lambda for the home team and lambda for the away team, and they use maximum likelihood estimation to estimate those parameters. But not only they estimated the parameters using maximum likelihood, but they also define a specific form that you have here, which is this one, which is basically a function of a constant, which means the team, the strength of it, the specific parameter as an intercept, and also the difference of the strength between both teams. So the difference between the teams will play in favor of one versus another, and some additional term here for the effect of playing at home. So they estimate those quantities from the bivariate Poisson distribution, and then they get the strength parameters as a new variable to put into a model. And then they have a bunch of other values for the game, like the time for the game and all of the things. They add these two additional variables within the model, here talking about a random forest for machine learning, and they were able to decrease the error of the model by some margin still. So what I just mentioned, for the different techniques, they may sound very separate, but each time the goal is still the same. They want to augment and improve the actual learning of the model, boost the performance of the model. It actually applies to any kind of techniques, as I showed, like for natural language processing, computer vision, or tabular data. And it achieves the same objective of giving more information. So we use actually statistical tools to extract specific information we're interested in and add that in the model for boosting the performance. And here, enhance in the term statistically enhanced learning really means this, like we want to improve the actual performance. Now, if we want to think of what are some properties or benefits that we can have from our model, we can use information theory and try to see how it could impact the actual model. So if you think of any model G, which is a machine learning model, which can be anything from the learning sphere that I mentioned earlier, it's just a prediction model. And then we have some first matrix XO with observed variables that we can have from a data set. And we also define a perf function, which is a metric which computes the performance of the model. So it can be the usual accuracy, the RMSE, any kind of metric we want to use. And so what we say here is that when we add new variables to the model that we name XS, with the S for SEL, Statistically Enhanced Learning, the performance will be improved by adding those additional variables. And the performance will be improved as long as the variables that we add to the model are relevant and still carry information, meaning that they are not independent from the other variables we're interested in measuring already. And to make this claim, we basically get back from information theory, where we try to see how the entropy or the uncertainty of a phenomenon behaves when you add more information. And so we take some theorem from Cover and Thomas, where they say that the entropy actually decreases, the information decreases when you condition to more variables, as long as the additional variables you bring are carrying information and still correlated to the observations you are interested in. We want to make a small disclaimer here, because we may think also of the R-square that are known, for example, in the linear settings for regressions, where by just adding more variables in the regression, you will just mechanically increase the R-square. Here is not the case, because what we're interested in is not as a function of the number of variables, but as a function of the information that the variables are considering. So what we have here is, if you add more variables, a bunch of variables that are still uncorrelated to the target variable that you want to predict, or the other variables, you will just do unnecessary things, and so the performance will just be the same. So if you have independence between the XO and the XS matrices, you will just basically end up with an equality here, which just means that you're not doing anything in terms of performance. One additional thing is the behavior when you have more variables and you have a more complex model, that the marginal information that you bring actually decreases. What that means is if you have a data set where you have hundreds of variables, and if you have another data set where you have 1,000 of variables, adding 2 or 3 more variables with the SEL technique, the additional information you will bring into the model will kind of be diluted within the bunch of other information you have. It's just that the additional information is getting lower. So in other words, the marginal information is decreasing or plateauing with the size of the data set. But we still have the inequality from the previous slide, where we're still saying that adding information will still help, but at some point we will plateau, and the additional variables will in a way be unnecessary because all of the information will already be carried by the other matrices. It's actually something we could observe from simulations. So if you think of a baseline, which is the blue line here, where you have a normal model with, like, let's say a random forest with data that you already know, we want to compare it with the benefit that we get from adding new variables from using the SEL technique, so statistically enhanced information. And what we see is that the lower the better for the red curve. So at the beginning, when you have a low number of variables from the original model, the additional information you're bringing with the SEL variables are actually quite interesting. But as you grow with the data set, you start plateauing and actually converging to the base model because the additional information you're putting into your model becomes very little. So now, if I want to go to more applications and see how we can use that for other use cases, I want to take an example of handball games. So for those of you who don't know what handball is, it's an indoor sport that you could potentially compare with football, but just playing with the hands. So the objective is still to score within a cage, but you are indoor and you're playing with 7 players, so much less number of people on the field. Why I'm taking that is, first, because I'm biased. I used to be a handball player, but also because these days we have the men's world championship running this week, and the final is by the end of the week on Sunday. So then what we may think of doing is, let's make the predictions of the upcoming games from the quarterfinals that are starting tomorrow up to the semi-final and the final. And of course, we use the SEM methodology to add more information and compare our model. And we also use something in the same spirit as what Christophe said, by extracting information to give a sense of potentially some quantities that would reflect the strength of a team. But also we also based on some other work done by Andreas Grohl also on handball, on how to model handball games with a similar technique. So what we have in our hands is information of past games, international games, so Olympic Games, World Championships, and also friendly games since 2019. But we also have information about the players, like the age, the height, the position of the different players within a team. And we also have information regarding the location and the competition itself, like importance, for example, because friendly games are much less important than the final of the Olympic Games, for example. Our objective here is to make a multi-target regression, which means we want to predict with one single model the number of goals scored by both the home and the away team. And for that, we use a boosted-based model, which is called CatBoost. So it's an equivalent of XGBoost or a gradient boosting model specific to categorical variables, if you wish. And of course, for that, we use SEL variables that we extract from past games from all of the teams. So for that, we use the Conway-Maxwell-Poisson distribution because we're interested in counting the number of goals scored by each of the teams. And we use this distribution, which is a generalization of the Poisson distribution. This distribution is particularly interesting because it can handle over and under dispersion, namely what consideration you need to have in the Poisson distribution is that the mean is equal to the variance, which is rarely the case in actual data. So we can use that for modeling under or over dispersion. This distribution is also pretty nice because you have some subcases where you can recover pretty known distribution. So for example, if you have nu is equal to 1, which means you have equi-dispersion, and so the mean is equal to the variance, then you recover the normal Poisson distribution, and you also have some other cases of the Bernoulli or the geometric distribution with some specific cases. Here what we do in our use case is that we take the number of goals scored by each of the teams. So individually, we take each of the teams' historical games, and then we try to fit a Conway-Maxwell distribution and fit that with maximum likelihood estimation. We then get two parameters, lambda and nu, that are the two parameters for the distribution, that we then use as additional variables to put into our model on top of the information that I mentioned earlier, like age, location, and so on. Just a practical illustration. You can see here the histogram represents the historical the distribution of goals scored by, I think it was for the French team, and then you have in the dotted line the actual fitted distribution with the Conway-Maxwell-Poisson distribution. So now if we see the features of importance, so this is the result of our CatBoost model, and you have a histogram that represents the importance of each of the variables within the model, namely how much you would lose when you remove one variable from the model. And what is interesting to see is that you have the new parameters that are our SEL parameters for the home and the away team being from far the most important variables. You also have the lambda home, which is the lambda parameter for the home team, which is coming as part of the top variables. And then you have the other classical variables that are coming. So then, if I were to make a bet today on what would be the future games, this is what I would present. So I'm not biased, my model did that, and I'm still predicting that France will win in the final and will be world champion by the end of the week versus Germany. But still, if there is any specialist of handball in the room, they would still complain that some results could be improved. For example, Denmark, which is potentially the strongest team in the world with France, of course, are not appearing in the quarterfinals. So there are still adjustments to come in the model, but still the results were kind of interesting. When you see Egypt, Germany, that are pretty strong teams, they're still represented over there. So I hope my predictions will be true for Sunday. So as a conclusion, SEL, as I just mentioned, is a formalization framework for different techniques for feature engineering for improving models' performance. It applies to any fields, any type of data, and what we try to contribute is by putting some structure and taxonomy on that, just to show that all of the things are actually connected. And we also try to prove and to show that using information theory, we can justify the use of this technique and why a modeler should spend a lot of time preparing the data before the model. And so as a next step, as I said, I still need to improve my model to make sure Denmark comes in the quarterfinals. And I have an objective of predicting the handball games for men and women for the 2024 Olympic Games in Paris, hoping to also see France as the Olympic Games for men and women. Another consideration is also potentially taking a deeper look into the mathematical aspects of the SEL technique by potentially studying the convergence of specific models or things like that. With that, I thank you, and I'm open to questions.